Hello, everybody. Welcome back today from my home office. So this week I want to talk to you about a very basic type of static analysis. And in fact, some people will argue whether it can be classified as static analysis at all. And this kind of analysis is called type systems. And we'll be talking about type analysis and sort of the methodology behind it, which is based on unification. That is a term that you may have heard of in your uh, previous studies. So I think there can be a larger debate about where type analysis ends and where static analysis starts. So I think most researchers will agree that they are fairly related fields. Some might even say they're just two views on the same thing. Um, and there's no clear-cut definition of the boundary between these two. Um, when I think about type analysis and static analysis, I basically mainly distinguish them with respect to their goals that they have, because when it comes to the methods, they can sometimes be quite similar and they tend to blend into one another, at least in recent years. So the goal of type analysis is, first of all, as the name suggests, to assign types to values. So values that you are computing in your program. Why is that important? Well, if you are used to programming in Java, let's say, then you are just used to the fact that everything is typed. Whenever you declare a variable, it actually has a type. If you program in languages that are a bit more low level, maybe such as C, that's not quite as clear cut. So there you can have also void pointers, for instance, that are pretty much untyped. But it's often useful to assign types to values, or sometimes it's even necessary, because ultimately the whatever you compile, it needs to be represented in machine code, right, to make it executable. And then the compiler needs to know what type of data it's actually dealing with. That's one reason for why you want to assign types to values. Another reason is to actually find bugs in your program, because if you perform operations on values and these operations are ill-typed, so they cannot be applied to the type of data that you're applying them to, then that's a bug, right? And that's something that, of course, would be nice to find already at compile time, not just at runtime. And so the goal of type analysis is really to prevent already the compiler from even processing ill-typed programs in the first place. So I showed you in the last week this little example in the Eclipse IDE, for instance, that would highlight if you're accessing a local variable that has not been assigned a value. That's something that would be a type analysis, right? So the type analysis would find that this basically, has not been assigned a value of a given type, and then it will notify you that this is sort of the type uninitialized. Because this is running before compilation, the design goal of type analysis is always that it should be very fast. So it should always execute within milliseconds or seconds in the worst case. As we will talk about in a few slides, this also means that we have to accept some false warnings by design. So type systems are usually designed in a way that they definitely prevent any type errors at compile time, or at least most of them. But they accept that they might also generate warnings in cases where the program would actually type correctly at runtime. In terms of the method, type analysis usually operates on an abstract syntax tree or on a very lightweight abstraction of that. So you barely see anything that generates a control flow graph or even a control flow graph across different procedures. That's usually not done at all. That's actually a big distinguishing factor. So actually all type analysis I know of, they are restricted to individual methods, and then types are assumed to be annotated to method boundaries. So whenever you have a parameter, let's say, or return type of a method, that is annotated with types. And so that's where the scope of the analysis ends. And basically type information between methods is communicated through these type annotations. And that's not the case in static analysis. In static analysis, we typically use it to optimize programs or identify bugs and vulnerabilities, and also aid program understanding. I would say these are still the key use cases today. Maybe program optimizations even less so today, although it's actually gaining a bit more traction right now with all these larger data centers that really can use a lot of optimization even just to save energy. Static analysis also strives for few false warnings. So some static analysis are also designed to accept false warnings by constructions, but typically the desire is to have as few false warnings as possible. And in comparison to type analysis, some static analysis at least consider relatively complex whole program properties, so properties for which you need the entire program or at least large portions of it to actually decide them. And the method, like I explained in the previous week, is that usually in static analysis we analyze certain data flow graphs that are built on top of control flow graphs. So we've talked about control flow graphs already and how you can derive them, for instance, from an intermediate representation. And in the next 2 weeks, I will be showing you how from that you can derive so-called data flow graphs as well. And these then directly encode the program properties that you actually want to decide. And yeah, so like I said, one key distinguishing factor is that in static analysis, you typically do not assume any typing annotation. So any program property that is determined by static analysis, it's sort of automatically propagated through the program and to the respective variables that hold these objects that have these properties. And there's basically little annotation burden on the programmer, so that the static analysis does not assume that you annotate a lot of code with type information or anything like that. Having said that, the fields are pretty related, and there are also blended approaches. For instance, there's the checker framework by Michael Ernst at the University of Washington, which has very powerful type analysis these days, and also works on approaches using annotation inference. So you don't have to write as many annotations as normally. And then these two approaches really blend into one another. And that's also why it makes sense for this lecture to cover at least the basics of type analysis as well. And that's not just my opinion, that's apparently also the opinion of Anders Moller, a colleague of mine from Aarhus University, whose slides I will be using throughout this lecture for this week. Talking about Anders, he's also a very devoted teacher, and if you look onto his website, which I've linked here, you will see information about a script that might also be useful to you. It's something that I've always sought to contribute to, but unfortunately did not find much time to get around to. So it does not cover exactly the topics that we are covering in this course, but there is a large overlap. And some of the approaches that I'm presenting here in a somewhat more informal way, maybe, they are formalized in the script. And so if you are wondering how these approaches really work and how they can be formalized, at least for some of them, you might find them in the script. So I encourage you to take a look. It should certainly be worth your while. Okay, so the scope for this week, like I already explained in the previous lecture, is the following. So we are assuming that we're given two inputs for the analysis. So a single method for the moment, not an entire program, just a single method independently of the others, and a certain program property that we want to decide. And we want to determine actually does this property hold or not. That's actually an interesting point. So in the next week, we will be talking also about so-called flow-sensitive analysis. They decide whether this property holds at a given statement within the method. For this week, we will actually be ignoring the statement. So we just want to know whether this property holds throughout the method or not. That is then called a flow-insensitive analysis because it doesn't consider the program ordering. It doesn't consider at which statements exactly this property holds. And not all, but many type analyses are designed that way. So at least the basic ones, they're all flow insensitive. Okay, so one way or one major task of type analysis is to actually derive type errors and present them to the users. And you can think about a whole number of reasonable restrictions on operations that you want to warn about, right? So, for instance, some arithmetic operators may only apply to integers, and you want to make that sure. Or you have comparisons which only apply to like-kinded values, right? So it doesn't make any sense to compare an object reference with an integer, let's say, at least not in most languages I know of. In C, you can actually do this, but we can argue about whether it's a good design or not. And in C-like languages, for instance, you also have the star operator, and that only applies to pointer types or pointer type values, for instance, and so on. And this is a non-exhaustive list. I'm sure you can think of more properties that are useful to be checked and that you have also already seen type errors about in your favorite compiler and programming language. Usually, and that should hopefully always be the case, violations of these rules, they should result in runtime errors. So no matter what programming language you are using, if you violate these and execute the program, then you should see some runtime errors. And some languages are more lenient here than others. For instance, JavaScript is a language that is pretty much notorious for almost never giving you a runtime error. It basically widely converts types into one another. I think most researchers by now agree that this doesn't make much sense and it actually hinders good programming. But it was just a design choice taken at the time. But if you look at more statically typed language, such as Java, for instance, then you may have seen things like class cast exceptions, for instance, that tell you when you have ill-typed conversions. The analysis also frequently run directly in compilers or integrated development environments. So, like I said, they need to be efficient and simple, and therefore they often sacrifice some precision. Then we want to do type checking, right? And so the question is, can type errors actually occur during runtime? And that's something that we would ideally like to decide already at compile time, right? So we would want to foresee whether the code that the type system is currently considering or the type analysis considering can have a type error when it executes. This is a very interesting problem, but unfortunately, there's a theorem called Rice's theorem, and it's really evil for the kind of research that we do, because that showed in 1953 that basically any really interesting property about a program is instantly undecidable. So all the research that I do in this space and that others are doing in this space, it's all undecidable. You can think, oh, that's disappointing. We are never going to be able to really solve this in full. But actually, I find that this is what makes this field exciting, because if there was an easy solution to it, it wouldn't be interesting, right? So the whole art behind a good static analysis is to design means that give you good results nonetheless, right? So that give you high precision and high efficiency and scalability of these approaches. And basically, get the best that you can possibly get for a certain situation, although you know that in theory it's all undecidable. So in this case, well, and also in all other cases, we have to use some conservative approximations, right? So here we say that a program is typable, so it's statically typable if it satisfies some type constraints. And I will be showing you what these look like. And these are systematically derived from the syntax tree. And if it's typable, then we want to give the guarantee that no runtime errors occur. Okay, so that guarantee we want to give you. But we accept by design that some programs will be unfairly rejected. That's also what some researchers called a false warning or false positives. So we're basically preventing some programs from compiling that are actually, in terms of the types at least, correct, that would execute at runtime. And this difference between what we would actually want to type and what we are typing with a type system, that is called slack. And what we will see next is the essence of a certain type inference technique by Damas, Hindley, and Milner. And that forms the basis of the type systems of some fairly strongly typed languages such as ML and OCaml and Haskell, languages that you may have heard of. And if you program in these languages, they're really notorious for strong typing. So it means you really have to make a concerted effort as a programmer to make your program type and compile in the first place. When you then are, or when you have been going through that hurdle and you have managed and mastered that, then you have a fairly high guarantee that the program is actually really doing what you want it to do because you have already spent so much time just assigning the right types. So it makes for very disciplined programming. But some programmers also dislike it because programming is maybe a little less flexible than in other languages. Okay, so just to make sure that we are all on the same page, so let's take a look at this graphic here. So let's assume that what's depicted by this yellow star-like structure are all the programs that are actually correctly executing in terms of their types at runtime. So they will not show any runtime type errors when you execute them. And like I explained, the static type system that we will set up, it is usually always designed in such a way that it's a subset, a real subset of this other set. Okay, so the number or the amount of programs that you are allowing to statically type is a subset of the runtime type system, you could say. And therefore, we get this guarantee that I was talking about, right? So if something types statically, it's guaranteed to be in the circle, and therefore it's also guaranteed to be in the surface of the star. But there's going to be a difference, right? So there are programs such as this one here, which would execute just fine at runtime, but because they're not part of the static type system, you will see a type error. And that difference, like I said, it's called a slack. And that's an eternal struggle, right? So we are always seeking to make the type checker a bit more clever. So, you know, a somewhat better type system, you could say, but maybe also a more complex one would be this one, right? So it has less slack and models this star structure even better. And of course, you can think of type systems that even, you know, go into these corners here. But because of Rice's theorem, we know that we are not going to be able to exactly, you know, fill out this star structure. So you're never going to quite reach it. There's always going to be some slack, and that we will just have to accept. So it is a struggle, but it's also a great source of publications, right? So like I said, it's a very interesting and active field, and people are always working on optimizations in this space. And in fact, there's been a lot of progress also in terms of type systems in the recent years. So by now, using type systems, you can decide much more powerful properties than we were able to do just a few years ago. And also you get away with a lot fewer type annotations than would have been necessary some years ago. So that's definitely exciting progress. Sometimes we also have type systems that are unsound. And you may not be aware of this, but this even exists in Java as a programming language. So really, most of Java's type system is sound. So you really have to make an effort to write code that will compile at compile time and will give you, let's say, a class cast exception at runtime. That's not quite so easy, but it is possible in one particular case, and these are so-called covariant arrays in Java. I won't be able to talk about this much in this lecture, but I encourage you to read up a little bit on this. And we might also be treating this in the exercise class. Suffice it to say that there was a deliberate pragmatic design choice in Java to actually make arrays covariant so that you can basically have subtyping on arrays. Although in terms of the type theory, it doesn't make sense. And in fact, you can write Java programs with just a couple of lines of code where you will get class cast exceptions at runtime, but this will not be caught by the compiler or by the type system because the type system is designed in such a way. Okay, for any type system, the internal workings are usually very similar, at least to what you see on the slide. So as an input, we will be given the abstract syntax tree. And out of this, as a first step, we generate some constraints. And I will be showing you some examples of what this can look like. And then we can use an off-the-shelf constraint solver that typically uses so-called unification. And then out of this, we get a solution. So either the solver will tell us this all types correctly, so the constraints are satisfied, or it will tell us that the constraint system cannot be satisfied. And then using current constraint solvers, it's fairly easy to extract a so-called unsatisfiable core. So these are basically the constraints that contradict one another. And then out of that, you can then generate an error message, which is typically what the IDE or compiler would then actually display to the programmer. And what's important is maybe about these constraints is, like I said earlier, in most type systems, at least, they do not take program order into account. Okay, so we go through the statements of the AST one by one to generate these constraints, but we don't do it in any particular order. So we could do it from the first statement to the last, or from the last to the first, or in any other order. It really typically doesn't matter. There are some few exceptions, but for most of the type systems that people talk about, it will be the case like I just explained. And then types, they really describe the possible values that you can have in your language, right? And here, just to show you an example, I'm showing you a very reduced set of types, right? Because I wanted to keep things simple, but you can think of type definitions such as this one here. So we can have a reference type, for instance, like you're used to from Java or some other similar languages. And an example reference type could look like this, right? So you could have a class constant. So that's actually a constant signaling that we're talking about a class type. And then we have a type name for that particular class. And then we can say any type in our program has to be, for instance, either an int type or a double type or some of this ref type, okay? Or we can also allow, for instance, field types. That's what we are seeing here. So you can also call this a record in C, for instance, or C++. So here we would have something of a ref type, and then a dot to signal that we are accessing a field or a record of this type. And then this can be followed by any other type, okay? So for instance, you can have an integer field or a double field or also another ref type field. And what you see down here, that could be a notation that we might use, for instance, to denote function types or procedure types, right? So for instance, that function would take parameters of these different types as an input, and it would return a value also of a type. And again, any of these here, these taus, they're just placeholders, right? So at any of these positions, you can again replace the type by any of the definitions that you see here. So it's a recursive definition, right? This can be arbitrarily nested. And then out of these types, you can generate terms using this grammar that I have here, right? So that's essentially context-free grammar, and out of this you can generate appropriate types, appropriate terms, and these terms then denote concrete types. So this would be one particular example instance here, right? So we have this function type down here, and it has been instantiated with this tau being replaced by an int, the last one being replaced by a class type, and this one being replaced by another class type. And the idea is now that we first generate really line by line through the program type constraints from the AST. And what's important here is that all constraints that we generate out of this, they are equalities. We will later on be seeing systems when we come to actual static analysis that are not equalities. But typically in type systems, we are dealing with equality constraints. And these then can be solved using a so-called unification algorithm. We also allow type variables. So these are placeholders for types that have not yet been resolved, that are going to be resolved by the unification algorithm. And here we are assuming that for each identifier declaration X, we have such a type variable here. And for each non-identifier expression, so for instance, something that is computing a number, let's say, we have such variables. We also make the assumption that all identifiers are unique so that they can be distinguished by the unification algorithm. And we also assume that the expression E really denotes an abstract syntax tree node, so not concrete syntax. Yeah, that just allows us to basically operate directly on types and not on concrete values. Because, for instance, if you're talking about an integer, you want to talk about any integer and not just about its concrete value, because that's not important here. I'm going to be showing you a very simple kind of type system here, because you can teach entire lectures just about type systems or entire courses just about type systems on their own. There are many extensions that you also know from popular programming languages, such as polymorphism and subtyping, and also type states and so on, and that I won't be able to cover in this course here. So let us see how you can actually generate some type constraints out of a little example programming language. So let's assume you can write expressions or type declarations such as this one here. We are explicitly saying that this variable I should be of type int. Well, if you define it that way, then it's quite obvious that the type of this variable I should actually be int, right? Similarly, we can assume that in the language we have integer constants. So this is a denotation for any concrete integer constant that you can think of, like 0, 23, 42, whatever. And any of these constants should obviously also have type int. Then this is getting a little bit more interesting. So here we are assuming we have any kind of operation onto values. So a binary operation, for instance, a multiplication or division, whatever, right? And here, let's think about this, right? So what do we typically want to require? So we want to require that maybe both operands, they actually are of the same type, right? At least for many programming languages, it's defined that way. And let's make that assumption here. So you can multiply two integers, but you cannot just multiply, let's say, an integer and a float. And then we would basically have such a type constraint here. And then if we have such a constraint, then it's also relatively easy to define what should be the type of the result of that operation. It definitely makes sense that the result is then also of the same type, right? So if you're multiplying two integers, your result is going to be an integer. If you are multiplying two floats, your result is going to be a float, and so on. So that's why we also have this type constraint here. For equality, we can make the assumption that the constraint is a little bit simpler. So like I said earlier, we typically don't want to compare pointers against numbers or anything like that. So a reasonable assumption would be that also the two operands here are of the same type. If we have an assignment, and that's interesting, then here we might also want to make sure that the left-hand side and the right-hand side of that assignment are actually of the same type. If you are aware of programming languages such as Java, then you may know about subtyping and polymorphism. So there basically you can assign a string type, for instance, to an object type variable. That wouldn't be a problem, but that is simply because the type system supports so-called subtyping. Here we are assuming a type system that doesn't allow subtyping, so we only have an equality constraint. We're assuming both have the very same type. And then also in many programming languages, if you have branches and looping constructs like you see here, so an if then else, for instance, or a while loop, these have the so-called void type. So they basically don't have any type because they don't return anything on their own, right? That's an important distinction. There are programming languages where this is different. There are so-called expression languages where statements themselves actually are expressions. So basically any statement that you can write, it returns something. So for instance, if you have an if then else, it will typically return the last value that was computed within the if then else. It's a certain design choice. Some programmers are fans of this, they like it, others don't like it. I personally don't have an opinion on it, but that's also not important here. Important is that depending on what kind of language you have, this may be void or it may also be not void. And then out of this, we are generating constraints, right? So I've already shown you basic constraints, but then here there are some more complex constraints for other cases. So for instance, if we have procedure call like you see here, then we will have type constraints that look like this. So for instance, we have that the parameter, the first parameter that is given here to this procedure call, it must be of this type x1, and the last one must be of this type xn. And then if this is this expression is denoted here by e, then this will have the type of e, so that's basically the return type of that. And that's then the entire type of that particular procedure here. Okay. If we have a new expression such as here, so something creating an object of class type C, well, then obviously the sort of return type of that new expression should be exactly class C. For null, that's actually kind of interesting. You've probably never thought about this unless you've heard about type systems before. But if you think about it, null in basically all programming languages I know of, it can be assigned to, at the very least, to any reference type, right? So you can assign null to a variable of type object or string or whatever. So that means that null is basically polymorphic, right? So you can assign it to any reference type. And therefore, null also cannot be really a type on its own, at least not if you have a type system that doesn't allow for subtyping. And that's why in this case, we model it just as a type variable. So we're basically saying this is an open variable. We do not assign it a type yet. It can be assigned to anything else. Here's an exercise that you can also try at home. So there's just a little program that's defining some integer type variable and assigning to it, and then that local variable x that's being assigned to a field. And as you see here, that's type compatible, right? So it's all of type int. But if you then try replacing c.f by c.g, you can actually think about what happens and what the constraints look like and how you would actually be able to identify a constraint error in such a type system. In general, this is being resolved through a constraint solver, like I told you about earlier. And such solvers, they really operate on such terms, like I'm showing them to you here. And these terms can be of a varying nature. So you can have sort of zero array terms. So these are sort of constant terms, right, like int. And then you can have n-array terms, like you see here. For instance, ternary term would be one that you see here, where you have, two input parameters and a third term for the return type. And then out of this, you can generate such expressions here, right? So if we assume that we have A, B, and C, which are zero array, and then we have, for instance, ternary terms like I, J, and K, and these others in between, then you can compose them like this, right? So you have, for instance, a unary term here that is called D, and that has a single argument because it's a unary term. And then you can insert this constant here, for instance. And you can, just through composition of these terms, replacing their free variables through other terms, you can get these composed terms that you see here. We also allow terms with variables, like I'm showing you here. So these would also be valid. And what's important here is that when I'm talking about variables in this case, like X and Y and Z, so these capital letters, here they are type variables, not program variables, right? That's important to understand. Has nothing to do with variables in your program. Here they're really type variables, so during the unification they will be replaced by other terms, or you could also say by concrete types, right? They're just placeholders for types. And then in the end, we are going to be solving this as a unification problem. And unification basically tries to determine an equality between two such terms with variables, right? So for instance, we could see it as a challenge to find certain assignments to these variables X and Y and Z that you see here, such that these two terms become equal. And there are certain solving algorithms that allow us to determine this automatically. A solution is then an assignment from variables, like you see here, to concrete terms, so terms without variables that make both of these sides equal. And such a solution is then also called a unifier because it makes things equal. And the typical method to get there is called unification. There's an implicit constraint that we and these unifiers always, or these unification algorithms always assume, which is implicit constraint for term equality. So that means two compound terms, like you see here, they are equal if all of their individual parameters are equal as well. So it's really structural equality that counts. And then during unification, you can have two types of unification errors. One is the so-called constructor error, where it may be the case that maybe the type variables actually match. So you would be able to replace X by the same constant A, let's say, for instance. But the constructors here, and these are called constructors, they don't actually match, right? So you still are not able to make these terms equal. You're never going to be able to do that. The other one is called an arity error, where you basically have two terms that may have the same name, but they have different arities. Depending on how you set up the type system, you can try to avoid that by construction. But if you don't do that, then you can have these arity errors, and that also obviously leads to a situation where this does not match, right? So it's not allowed to simply ignore this particular parameter. You cannot, just void it, null it out, and make this equal. That would be against the rules. We will then, after a break, be discussing the linear unification algorithm. So that's probably the most basic and foundational algorithm in the space by Patterson and Weckman. It's really nice because it runs in linear time and it finds the most general unifier or decides that none exists, right? So if you actually have a type error, for instance, and that can be used as a backend for type checking. And I guess many implementations also do use it. Some of the more sophisticated type checking algorithms these days, maybe not anymore. But you can only use it for finite terms. But for what we have been discussing here, that should be sufficient. And yeah, like I said, we'll be taking a short break now, and I'll get back to you with an explanation of how that works. Thank you very much.